And now it's time to hear from Cometh and from Jerome the Tychey. He's the CEO of Cometh and also is the president of Ethereum France. And
1, 2, 1, 2. Does that work?
yeah.
All right.
Let's go. Woo.
Are you ready to make history with a capital H? Woo!
Yeah, we're ready.
Okay.
Good. Yeah, just I want to say something more about you, that you are also an associate professor in economics at CNAM, an engineering school in Paris, and as a fun fact, he was responsible of a large reorg on the Ethereum proof of work testnet in 2016, and he feels sorry about it. But yeah, that's something very interesting. Let's go.
Indeed, it's getting harder and harder to find the testnet ETH, right? So I started my career in the ecosystem by doing some mining, and at some point I wanted to have a lot of ETH from Robston, and what I ended up doing is just putting my miners on the testnet. Well, here we go for the reorg. So I'm here to present to you one cool byproduct of Stylus, one cool byproduct of the fact that we have now an alternative VM in parallel of the EVM that is super powerful and can run super fast. So I was already introduced. If you're looking for me, I have the same handle everywhere, JDETYCHEY. We're hosting ETHCC. I hope to see you there. If you enjoyed DEF CON, there is a similar event as DEF CON happening every year in France or around France. So hopefully see you there next year, late June, early July for ETHCC Cannes. And Cometh is a company that's been in business for about 4 years now. We are soon going to celebrate our 4th anniversary. We do account abstraction most of the time and things around account abstraction. And what I'm going to show you today is something that we can use in account abstraction. That was the initial motivation of building something like that. And we work with companies like Gnosis Metri, WorldCoin. Cosmic Battle is our latest game, because we have a game studio inside the company that runs on an L3 on top of Arbitrum. So we are like piggybacking of what we are building inside the company. And this QR code here leads you to a Connect kit that is account abstraction in a Connect kit on a cool website done by Keiko, where you can get on-chain price on Arbitrum. Institutional grade on-chain price, because they are signed by Keiko on Arbitrum. So I'm going to replicate only on Arbitrum. All right. It's not using Stylus yet, but yeah, that's a good thing we can do around Stylus with this. Actually, having a powerful VM let us also write weird or not EVM-based cryptographic curve like SegPit56 R1, and we should use that for that. Okay, so now onto the real business. How to build a permissionless multi-chain indexer for EVM blockchains, and also non-EVM blockchains. So it can also work for non-EVM blockchain. This should be noted. It works really well for proof of work blockchain, but yeah. So throwback from February 2024, our team was in Denver for the hackathon done by Stylus, by Arbitrum, notably on Stylus, and we worked on the first prototype on this. Back in the day, it was called Storbulus. We have a new code name for this project now, and it won a couple of awards during the hackathon, and it got us interested in pursuing this kind of work, open sourcing it, and hopefully convince other people to help us build that. Well, again, I'm quite humbled to be here today because, well, what I'm seeing around the Stylus ecosystem and all the different development that is being done and the amount of brain juice that is being powered into this ecosystem, the thing that we have been building is just a pretty cool utility, but it's not rocket science, so it's hard to execute. So hopefully you will be interested and keen to help. So here is for the problem. Like we had a few questions from the previous talk about how exactly does it work on the Arbitrum Stylus side? Like, is it a precompile? How do you access the precompile? About the EVM? What is the EVM? And so on. You can ask me some deep question about the EVM. Not too much about deep question about Stylus. I can answer a few of them. But one cool thing, or what not cool thing about the EVM is how much history we can access. So did you know that when you are speaking to your smart contract, asking him to retrieve data from the blockchain, the only data it has access is the data from the previous 256 blocks. Did you know that? Well, you came to the right place. right? You learned something today. So there's no way to access previous Ethereum state, nor transaction hash, nor anything at past 256 blocks. And that's quite a problem, and there's an EIP coming in, the Pectra hard fork, that's going to help, 2935. Those kind of EIP that you don't really read about. You're like, oh yeah, historical hash, blah, 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 blah. It's going to help from the history query perspective, but it's not going to be full. You only get 91, 92 blocks, not 256. That's a bit better, but not so great yet. So this is going to help a bit, and still a lot of chains are going to continuously face this kind of problem, and the non-EIP 2935 chains are also going to face this problem. But yeah, well, okay, what is it used for? What do you want to actually access a lot of data this way? So there are use cases in DeFi, in airdrops, in cross-chain interactions that can be leveraged from that you can do for that. You can also confirm the user ownership of an asset across chain or at a certain period of time. You can also prove that you've been using a protocol by saying like, hey, this is a transaction that I interacted with the protocol back in block number 23, and we are at block 10,023, so you're able to prove this kind of thing. You can also prove to be the owner of something at a certain point in time, because you're like, hey, at this block I was the owner of that, so I should get this or get that. From certain protocol perspective as well, when you are bridging out of, if you're in the Arbitrum ecosystem and you are bridging out to another thing in the Arbitrum ecosystem, sometimes you get a super cool boost and the bridging out is instantaneous. But most of the time, it's an optimistic bridge that you have to accept the delay. Having a proof that you actually own the asset that you are trying to bridge out or bridge in is going also potentially help the interaction between bridges and across cross-chain protocols. For us, as an account abstraction-focused company, it helps us on managing smart accounts across different chains. And this was the initial motivation on working on that. And honestly, storing a lot of stuff on-chain, now that we have access to a lot of block space, is kind of exciting. Like, we don't know yet what we are going to do with everything that we store in terms of history, in terms of things. We have a few ideas that I've tried to put there. But there's potentially many other applications that are going to pop by the fact that we are now able to store historical block hashes of multiple chains at the same place. Or just lightly, if you are an L3 that very frequently interact with the L1, well, why not storing the history of the L1 on your L3 since you have a lot of space, and look at this history to do something. So what I'm going to get into more details now is something that if you are running an L3, you can also think about that as something you can run on your own chain in a very lightweight manner, just saying like, hey, I'm also indexing Polygon because I want to do things with Polygon, and Polygon is talking to the L1. And I'm also indexing the L1 because I'm oftentimes looking at what's going on in the L1 to do something in the layer 3. One cool application would be like if you are running a chain called Ape Chain and doing things if letting you stake if you have an NFT on the L1. With this kind of approach, you are able to prove that someone actually owns the Ape NFT that you want to give staking on the L1 to the L3 directly, just by having access to the Ethereum hash history on your chain. I promise there won't be a deep dive onto Rust codes and so on, mostly illustration like this. So this is what we have access to right now. The block number n-256 and the latest block. This is what's available at the moment. What we propose is give a way of actually accessing the whole history of blocks from 0 to, the latest. And what we are going to use is storing the block headers. So everything that you see, oh, I got a pointer, yeah. It doesn't really work, okay. Everything that you see here, previous Ethereum block headers, parent hash, beneficiary, difficulty, gas limit, and so on. There's different ways of representing the block headers depending on the fork that you are considering. After the Beacon chain launch and the switch to proof of stake, the block headers have slightly changed, but you're able to store everything. So you're storing the thing in this rectangle here, and inside the transaction root here, you are able also to say, hey, this is a transaction that's part of the transaction root, because this is a transaction, that's the rest of the tree, and it matches the transaction root. So let's store everything here. So one cool thing about Arbitrum is that we get the Arbitrum receipt that let us know about what's going on in the layer beneath. And from what we see in the layer beneath, we are able to interpret that, okay, we should take this Ethereum block to the L2, take this Ethereum block from the L2 to the L1, and now that Arbitrum just sequenced inside the L1, we have access to the latest L1 blocks that Arbitrums know of. Which means that from the indexer perspective, we have block number n and probably block number 5, and we can just fill in the gaps between these previous blocks and these latest known blocks. And by filling this gap, we have a recursive way of proving that this is the right block because they hash together from one another. So you are just furnishing the whole history until the block that was lately known, and voila, you have access to the L1 history from your L3. But we can go a little bit deeper. That is, if you are an L3, and you're like, well, I need to really access the Ethereum history really often time because I have this specific use case of just checking if this ape is actually owned by this guy so I can give him access to this, this, and that. You can run this in a lightweight fashion, but you can also consider that we can create a greater good on running an L3 where we store everything. Yeah, let's have a copy of everything. Let's have a copy of the whole L3 history of all the L3s on top of Arbitrum. Let's have the history of Arbitrum available there. Let's have also the optimism history. Let's have also the base history of the superchains, and so on and so forth. You can store everything inside this L3, so you can start to think about constructing proofs that something happened on one layer to another layer. Because all of those layers eventually communicate with the L1. And when I was mentioning EVM chains, it turns out that we can actually also index blocks of proof of work chain very trustlessly, because from a proof of work perspective, we are looking at the block headers and verifying if the difficulty and the nonce produced are actually matching the expectation of the protocol. So you can continue to hash to prove the block headers of Bitcoin, of Dogecoin, and so on and so forth. So with this kind of approach, we propose a novel way of storing everything under the same roof. And potentially, if you are specifically interested by one history, you can also replicate it on your side. We're given the code name 0xv because the decimal of the chain ID that we are using it on is actually 4078, which in hexadecimal called 0xv. If you go on 0xv.io, you have a full presentation of how it can work and how it does work and so on. So, okay, what do we get from that? Let's say that you are either on your own L3 with access to the history of the L1 and the different chains that you are interested in. And now let's take it to a broader generalization. You have access to a node, or you have access to an RPC endpoint. Well, we have access to an RPC endpoint of layer 3 on Arbitrum, where all the history of a lot of chain, let's say the history of all the EVM chains, is actually stored on this place. Now you're able to generate storage proof, which are proofs that a certain transaction is included in a certain history. Let's take it this way. A contract is asking me to prove that I send a transaction to the Uniswap V2 contract. If you remember in 2020, if you had interacted with the Uniswap protocol, you were eligible for a 400 airdrop of Uni token. If you wanted to give a proof that you actually interacted with that, the way to do it is give me a transaction that is included in a block. So transaction, transaction tree, transaction root, and give me the chain of hashes from this block with the inclusion to the latest block I know, the latest block I can request. So that's exactly what you get with an indexer using Stylus to generate those proofs. We look at the whole history that we have access to, and we generate a trail of hashes that you can port to any contract for interpretation of, yeah, indeed, if this person is able to show me that this transaction is included in a block with a hash that matching with the recursively hashed together to the last block I know, well, if someone is able to construct such history and such recursive line of hashes, it means that this transaction was actually included. If this transaction was targeting this contract, well, it shows that this person has interacted with this contract. So storage proof refers to the fact that this transaction is included in the history of an EVM. Now, that's from the L1 perspective, but we can extend that by the fact that we have access to multiple different history of different L2s, L3s, and so on and so forth. And all those layers, at some point in their life, actually every time they sequence, they hear about what's going on the layer beneath. So you can actually compute proofs that something was included in Arbitrum. This refers to the state of Arbitrum that was appended to the L1 on a certain block. And whenever Optimism talk to the L1 again and hear about a later on block, you can actually give a proof to Arbitrum that to Optimism that this transaction was included into to Arbitrum, that appended into this block of Ethereum that you know of. And so from the Optimism point of view, you're like, yeah, indeed, I heard about this block, and this previous block must be included since we have the trail of hash, and this previous block actually contained the state of Arbitrum, and in the state of Arbitrum, I have this transaction included in the state. Well, they are optimistic, those proofs. They are optimistic in the way that you need to wait for the layer that you want to verify the proof on has heard about a later block that happened at a later stage from where you have included the transaction in the first place. They don't tell you much, but they tell you already a lot. If you heard about state proofs that are a little bit more fancy, the state proofs are giving you a proof that this transaction is included and that the state have changed from this point to that point. They are extremely powerful. They give you exactly what the transition was, how it happened, and so on and so forth. The problem from state proofs is that they rely on zero-knowledge technology that requires you to convert the state of the contract that you are interested in into a circuit and generate the proof on top of. Yeah, no code, but we are getting into this type of proofs. What I like to compare state proof to storage proof is in the history of the space race, when the first tryouts of flying without gravity, the US realized that if you don't get gravity, you don't get ball pens to work. Like, the ink needs to go down. So they spent about $2 million and something of back then $60s, in the $60s, to construct a pen that writes in every single direction. So that's state proofs. It's complicated. You need to convert things into a circuit. You need to build a lot of things around that. And eventually, you have a proof that the state changed after this transaction. It's big. It's costly to generate and cheap to verify, or cheap to generate but costly to verify. You need to find things and so on. In this case, you can consider the storage proof as the approach of the Soviets. We send pencils, like things that are super easy to write on every direction. Even if you don't get gravity, you get friction, and that's enough. For most of the use cases that we could think of so far with those kind of approach, the storage proof are quite enough. So they are bringing some diversity into the ecosystem. It's like it's a different approach than the ZK approach. And furthermore, if the EVM transition to a fully provable ZK EVM, then you get the benefit of state proof as well in the same way. It's also easier to extend and use. They're available. It's just mixing different hashes. They're super cheap to mix together because they are precompiles. And you need Arbitrum stylus to generate those proof and store those proof and order those proof and index those proof in an efficient manner, but you don't need stylus at all to verify them. You just need access to the already available hashing functions on the different layers of Ethereum. So it's very simple to get a proof. In our current implementation, you just get a proof by appending the transaction that you want to prove the inclusion and the block that you want to verify it on. You can also consider a next step as a proof of inclusion from this chain to that chain. Think about the multi-chain indexer as capable of reading what is the latest block that this specific chain knows and that origin chain knows, and computing the trail of hash necessary. And in the midterm, we can do pretty cool things, potentially, like having the Graph API directly on-chain. which will require to consider your contract that will be targeted by this indexer as a stylus contract, speaking to the indexer and indexing the thing that you want to do. And potentially what's interesting from a decentralization perspective is that every chain that gets indexed on a shared layer, doing indexing for all the EVMs, is actually acting as an emulated light node because you have access to everything, it's there. So it's giving resilience also, providing us from being a glorified database. So we did a demo of the utilization of those storage proof at ECC last July. It showed the application of that kind of approach in a chain abstraction on top of account abstraction approach. The approach here is to say that you have a primary safe, a primary smart account deployed on Arbitrum, and this primary smart account is controlling a secondary smart account on Optimism. So we want to say that any addition to the list of owner of this safe on Arbitrum should be reflected on Optimism. So that's a pretty nice use case for storage proof specifically because in the context of having your smart account on one chain, having your smart account on the other chain, you know the code of those two contracts, you trust the code of those two contracts. So if you consider that the primary safe has received an update, then this update should be applied to the secondary safe as well. And yeah, this is working. You can check you can find easily the demo on the archive of ECC, and we're going to continue digging on that. But we feel like the use cases don't stop at all at the account abstraction aspect. There are many other things that we can build on having a multi-chain indexer. So, well, that's all I have for today. I'm leaving 3 minutes and 30 seconds for the questions. If you'd like to help us build this out or ask some questions, you can easily find us, reach out. You can find more info on zerexv.io, and this is an article that one of my colleagues, Johan, wrote of the initial implementation. And yeah, getting there, we are indexing chain histories. Thank you, folks. We have done some questions. Wow.
Great. I believe you explained it so well that there's no questions, but thank you very much, Jerome. It was amazing.
Anytime. Well, guys, enjoy the DEF CON event and the Arbitrum event, and hopefully see you at ECC in Cannes.
Yeah, for sure.